So today I want to keep talking about broadcast. So remember, last week we talked about reliable broadcast and uniform reliable. So remember, reliable broadcast means all nodes or no nodes. Get it? We did different forms of this. We're using perfect or eventually perfect or even no failure detector, which is just a question of efficiency. We also looked at uniform reliable. Uniform means that if a failed node delivers, all correct nodes deliver. So uniform means failed plus correct nodes. So uniform is a style. Many distributed algorithms have regular versions and uniform versions. So the uniform version means that if it works for a failed node, it has to work for the correct node too. Whereas the non-uniform version, it doesn't worry about the failed nodes. Okay? So for the reliable broadcast, how do we arrange that? How did we arrange that it worked? So when it delivers, when a failed node delivers, all correct nodes have to deliver. So we did that using this function, which basically, and a perfect failure detector. So if all correct nodes get acknowledgements, so basically we wait for acknowledgements for all the correct nodes, they got the message. And since we have a perfect failure detector here, so this is, we know that this set of correct nodes, that there's no mistakes. So all the failed nodes are removed from that set. Okay, they will be removed from that set. So the real set of correct nodes can be less than this, but not more. You see? So maybe there's a failed node and we did not yet get the crash message. So that means the correct set we know here is like a higher approximation. Huh? It's upper bound. The real correct nodes can be less than this, but not more. That means if this condition is true, then it's also true for the real set of correct nodes. Okay? So that means we can deliver it. So with that function, we can make it work. Yeah? With a perfect failure detector. So basically, all the nodes, all the messages are pending until we get all these acknowledgements. We have this can deliver connection. Okay? So that we saw that last week. I want to make one extra addition to that. So we can show that this is correct. Okay? So the algorithm we saw used a perfect failure detector with the correct nodes. But can we do it with weaker? Remember the reliable, we did it for eventually perfect and even for no failure detector. We'll actually do it also for a no failure detector here, but we have to change a little bit the algorithm. We can make it work also for no failure detector. Okay? And we're going to use a technique that is very often used in distributed algorithms. So the first time in this course, we're going to talk about majorities. So we're going to assume a majority of correct nodes. That means if we have 10 nodes, at least 6 have to be correct. Or if we have 9 nodes, at least 5 have to be correct. So if we have a majority, then we can get it to work with no failure detector. And it uses a very interesting trick. Okay? So this majority idea is something that's going to come back. So this is the first time we're using it in the course. So if the correct nodes, if there's a majority of correct nodes, then we can do the following. We will also get acknowledgements. Okay? We will do just as before. We can only deliver when we get enough acknowledgements. Okay? But what does enough mean? Since now we don't have any failure detector, we can't assume that all the correct nodes get acknowledgement. Well, enough means we get a majority. So we get acknowledgements from a majority of all the nodes. Okay? So what does that mean? How does that work now? It's very interesting. So basically the function can deliver, instead of saying all correct nodes get acknowledgements, all we have to say is that the number of correct nodes, so the cardinality of this set, is greater than n over 2. We get a majority of acknowledgements. And if we do that, and if there is a majority of correct nodes, so this is the failure condition. Huh? If there's a majority of correct nodes, it will work. Okay? And how does that work, this trick? It's a very interesting trick because we have two majorities here. Huh? We have a majority of correct nodes, and we get acknowledgement from a majority. So we have two majorities. So a majority of correct nodes, a majority are correct nodes, and another majority, we get a majority of acknowledgements. And the trick is that the intersection of these two majorities has to be non-empty. Okay? At least one of these acknowledgements must come from a correct node. Okay? At least one, because we have a majority of correct nodes. So these two majorities are different sets of nodes. Okay? They have nothing to do with each other. They can be completely different sets of nodes. All we know is that the intersections of two majorities is non-empty. And that means that at least one of the acknowledgements comes from a correct node. Well, if there is one correct node that gets the message, that correct node is going to do a best effort broadcast. And because it's correct, it will guarantee that everyone gets it, okay? So the trick is that there's at least one correct node doing the best effort broadcast. So that's how we can get this uniform, reliable broadcast to work, even with no failure detector. But it's not as good as the one with P, huh? The one with P will work even if there's n-1 failures. But the one with no failure detector assumes a majority of correct nodes, means we can have less than n over 2 failures. So we're paying a price. Here we can have everybody fail except for one. It still works because we have a strong P detector doing all the work. But if we have no failure detector, we have to give it up. And we can only accept less than half failures. If we have more than half failures, we don't have majority of correct, then this doesn't work. Okay? So you see the trick? We can get rid of the failure, we can replace the failure detector by another assumption that we have a majority of correct nodes. Okay? And then we can prove it's correct. So that's the last thing I want to say about reliable broadcast. Okay? You see that trick? You see how it works here? Okay. Remember that trick because that's a really important trick for distributed algorithms. So we're going to use it over and over. And in the course, it's a very important trick.